Okay, so welcome back. Now we consider examples which are more larger than what we have discussed so far. Again, we will be seeing control unit and data path. So one is greatest common divisor or GCD, and the other is a 32-bit processor, which is called beta. Okay, so let's see how GCD algorithm works. So basically this is the behavioral code of a GCD algorithm, and this is a code which may not be synthesizable, or it may be synthesizable. We have to check that, but this is a high level code. Okay, so it uses this in fact this is non-synthesizable, because you see there are these values, but there is no pause edge of clock. So this code is unable to infer any register. So this is code only fine for simulation. If you want to run it in model sim, it will work, but if you want to synthesize it, it will fail. It will definitely fail. Okay, so but let's see what the algorithm is. So if we have two numbers, a and b, and we want to find the GCD, the algorithm says that if a is less than b, okay, what we do, we swap a and b. Okay, so if a is less than b, we swap it, else we check if b is not equal to 0. So if b is greater than 0, we say a is equal to a minus b. Okay, else if b is equal to 0, then we are done and the algorithm finishes. Okay, so this is the whole loop. You can try this algorithm. You can take two numbers and you can apply this algorithm. So whenever a is less than b, you swap, then you subtract, a is equal to a minus b. If b is not equal to 0, you continue, and when b becomes 0, then then you stop. Okay, so this is the algorithm for GCD, and then at the end you say y is equal to a. So a contains your greatest common divisor, and this is your output. So normally this is the first step of an algorithm, and you can do this in, mostly people do it in C++ or C, or you can write it in MATLAB, or you can write it in a behavioral level non-synthesizable Verilog if you are comfortable with it. And if you want to simulate it, you can simulate this non-synthesizable code. So you can write the test bench. You see there are no ports. Then you can instantiate it. Okay, so this is the instantiation of the code on the previous slide. Then we have our initial block, and you see in the initial block we say a_n is equal to 27 and b_n is equal to 15. So we are taking these numbers and we are interested in what is the greatest common divisor of these numbers. And you see there are system directives. These system directives read from the command line. So $value, $+ arguments. If you use this will give you a prompt, a black screen with a prompt, and it will ask you to enter the value of so this is from command line. So when you want to execute this code, you can write the name of the executable and plug it in with values. Okay, so then you insert a delay and then you display. So here are the inputs, then you apply the algorithm, and here are the outputs. but this is non-synthesizable. What if we want to actually synthesize it in hardware? We need something like this. We need a control unit, and we need a data path. So we need an FSM and we need an data path. So the GCD RTL will look something like this. But let me first come to these slides are slightly misarranged. So let me come to this point. Okay. So this is the control unit or FSM, and the bottom one is the data path. So as we saw in the algorithm, which was something like this, but this is more a C style code. So we can easily see that we need two registers in hardware. We need a register for A and we need a register for B. So here is our A register with clock and everything. Here is our B register. So we have two registers. Okay. Then we have which operators we have. We have subtract. So subtract operator is here. This is the symbol of ALU with this this triangle, this notch. This is a symbol of ALU, and in this case it is implementing subtraction. This is the only operation. And then we have this one, which is A less than B. So it is basically this one, A less than B. Okay, so little than B. And then we have this one. This is another operator. It is here. So it is basically the comparator. Okay, so I think that that's all. This is what we need. So obviously you see we need to initialize A. So when we need to initialize A, it means we are sometime putting the value of A from outside, and sometime the value of A is basically this one, which is this line, which is A is equal to A minus B, and this is coming from the subtractor, okay, with the mux. So we need a mux here. This is the 0 line, this is the 1 line, this is the 0 line, this is the 1 line, this is the 0 line, this is the 1 line. So in initialization, you see this is our A mux. This is the name, and the select line is called A mux cell. This is our B mux, and the select line is called B mux cell. Okay, similarly this one is out mux, and the select line is called out mux cell, and all these select lines are controlled from the FSM. Okay, so you can see all AMUX cell, AMUX enable. So this is basically the load enable, as we discussed earlier. Similarly, this is the load enable of B, which is B reg enable, A reg enable, B reg enable, and these are the two outputs from the data path that go into the FSM. These are basically the flags or the signals on which the FSM decides. So one tells if B is 0 and the other tells if A is less than 0. And based on this information, the FSM generates different control signals for the mux select lines. Okay, so this go is for initiating the control unit, and this done is basically a signal that tells the user that GCD has been calculated, and the result of GCD will be in A register, so the user can read it from there. Now you see that in order to run this algorithm, for example, we have different states. So the first thing I told you in order to design an FSM is to recognize the states. So the first state is, if you come here, again I told you that the code is slightly, the slides are slightly misarranged. You should always have a load or initialization state. So this is our first state, which is load, and you see in the load state, A enable is 1, A enable is 1, which is this line. So we want to store something in register A, okay. Similarly, because we want to initialize A. Similarly, B enable is 1 because we want to store something in B. So A in and B in are to be stored, and you see that A mux cell is 0 because we want this line to be active, and similarly B mux cell is 0 because we want this line to be active. So we want to store these values from outside into register A and B in the initialization state, and the value of outmux does not matter here, and done is 0. This is just the initial state of done because we have not completed anything. So the first state is load. The second state is this one, which is swap. So swap is our second state, and in swap what we do, whatever is stored in A that goes to B, and whatever is stored in B that goes to A. So how this is done, so you see A enable and B enable are active, and the A mux cell is now on 1, so it is selecting this line, and the B mux cell is 1, so it is selecting this line. So you see that the output of A is directly fed to B, so A is stored in B, and you see that somehow we can check that how B is stored in A is here. So it goes into this line, okay, this line here, and from here you see this this skip line which skip the subtraction, and you see out mux cell is 1. So pay very close attention. When out mux cell is 1, we are skipping the subtraction, and on this line we will only have B, and B goes to A, so A will be stored, so B will be stored in A. So this is how the subtraction is skipped and B is stored in A. So when we have the swap state, we have 1 1 1 1 1, and done is 0 because we have not completed. Then we have the third state, which is subtraction, and let's see how the subtraction states works. So first you have to check that B is not equal to, so this is our third state, so we have to check if B is not equal to 0. So you see in this state we are doing A is equal to A minus 1, so we are not storing anything in B. So that's why you see that B enable is 0. So we do not want to change or we do not want to store anything in B, any new thing in B. So whatever is in B stays there, okay. And the A mux cell is on 1, so we are on this path, okay. We are selecting the second path, and the B mux cell is X because we do not store in something in B, so it doesn't matter if the B mux cell is 0 or 1. And the out mux cell is 0, which means that A will be coming from here, B will be coming from here, and A minus B will be appearing on this line. So we will be storing A is equal to A minus B in A register. Okay, and at the same time this is combinational logic, so this is always done in parallel. This logic is always active. So whatever is on the A and B line, this logic is active. So B is compared to 0 and the flag is generated to control unit. And the last state is the done state, and you see in the done state again everything becomes so the done signal becomes 1, and the A enable and B enable becomes 0, and others becomes don't care. So this is the full control table, and from this control table we can very easily determine the signals. So for example, we can say because these are 1 2 3 4 5 6 bits, we can define a 6-bit ridge is our control signal, and we can just assign this using a concatenation operator, and we can say in the order in which they are listed in the ports: A in, B in, A muxil, B muxil, out muxil, done. This is equal to control signal, and our control signal is defined in this block. So this is another style of FSM coding. Remember the one style in which we have the 4 parts. This is another one which you can do for simple FSMs like these ones. So always at star. So this is the control logic. If not running, control signal is this one. So if A is less than B, this is the swapping, or to be more clear, you can use these names. So let's look at what is not running state. It is 1 it is this one. Okay, so maybe we call this if state is we can say it like this: if state is equal to load. And we have already defined load with the parameters. So remember from the previous style that we use parameter to define the state coding. So we can say if state is equal to load, the control signal is these 6 bits. Else if it is swap, so A little than B is the swap state. So then it is 1 1 1 1 1 0, so it is then this one. And if it is B is equal to 0, this is basically the subtract state, and it is 0 1 0 1x 0 0, so you see this one. Okay, and last is the done state, and it is 0 0 x. So you see it's quite simple to write the code. This is again the full diagram, the test harness. Where is the code? Let me go through the code, the complete code. I think it's on here. I told you the slides are slightly misarranged. So this is the data path. Okay, so you see the data path. It has, let me draw these figures so we understand more clearly what is going inside and outside. So this is the clock, and then A in, B in, A mux cell, B mux cell, and let's say out mux cell. These are the inputs. Then A in, B in, these are multiple bits. Then output is B0 and A little than B, and then the final output is our result, which is Y. And if we check the control unit, let me draw it again here. So it has a clock, it has reset, it has a go for initialization, it has a B_0 that is coming from the module, it has a less than B, which is coming from again the data path or module, and then we have several outputs. A enable, it is going to module. B enable, it is going to module. A mux cell, it is going to module or data path. B mux cell, it is going to module data path. Out mux cell, it is going to module or data path. And finally we have the done signal. So this is our FSM. The above one is our data path. So this is how they are connected, and let's see how they are coded. So after defining all the inputs output, you see assign y is equal to a. So a is the one of the registers, and we have two registers, A and B. So let's see how registers are defined. You see this logic in red box. So always at pause edge of clock begin if A enable. So if A enable means it's equal to this. If A underscore enable is equal to 1, they are the same thing. A gets non-blocking and next. If B is equal to B enable is 1, then B gets next. So you see for each of these else there is no F. For each of these F there is no else. That's why on the else part what will happen, it will happen like this. Else A is equal to A. So basically the feedback will happen. I told you that it is something like this, that it is D, Q, and we have a mux here. So whenever we have a load enable line, we have this kind of logic. This is our load enable, this is our D, and this is our Q, and we have a box around. So this is called load enable register. So this is how we code a load enable register. Okay, and then we have several muxes. So for example, I can say out is equal to, so out is that line. It is equal to, or let me go there to the other diagram where we draw. So out is basically connected to A. Okay, so let me see the code. Oh, is the code? Okay, it is here. Out is equal to okay, so this is not, basically there is a mismatch between the code and the diagram. Okay, so this is not out, this is Y, and out is this one. This line is our out. Okay, so for that out, you see sorry for moving forward and backward. So out is equal to based on out mux cell. If it is 1, then out gets B, else out gets B minus 1. So this is, and remember that bypass mux, and the same goes for the other muxes. You can just look at it and you can write the code. And similarly for the logic decision part, it's very easy to write the code. So you see the data structure, the data path part is very easy to code. Same is the FSM part. So we have defined all the input, and we say this is the logic that was missing on the one of the previous slides. So a reg running is equal to 0. This is basically a register always at pause of clock. If go running is 1, if else if done. So this is basically a register, and this register is called running, and it tells when this is 1, then the circuit is running, the GCD is in running state. Else if it is 0, then we don't need to do anything, and that is checked here. Okay, so basically when you come to when running becomes 1, so this is basically the first time. So this is basically the loading part. Okay, and in the loading we load the table that we already discussed. So now it makes sense. This is the complete code, maybe the complete code where both are instantiated. Maybe it's somewhere down, or yes. So this is the test harness that we discussed, I think, or you can go through this. Yes, I think we have all. These are all the slides related to GCD, and I think we have discussed all the slides in detail. Let me check if I have missed something that is relevant to GCD. No. So this is the detail about GCD. I hope that with these few examples, so we have, let me summarize these examples. First, we discussed the factorial program and how we map it into hardware. Remember that in the initial lecture I told you that the goal of this course is algorithm to hardware mapping. So now you are beginning to look that what I was talking about. Okay, we are mapping different algorithms that are meant to be run on a desktop, PC or laptop or personal computing. Now we are designing a very custom hardware for them. We may need this hardware for maybe for speed, maybe for reduced area, maybe for reduced power consumption, and we can play around with so many different factors to improve it with one aspect or another. So this is basically algorithm to hardware mapping. And so we discussed factorial, then we discussed a parallel architecture for factorial. We discussed a single cycle architecture that is programmable. So we discussed a microprogram state machine. Then we discussed the GCD and a custom architecture for GCD. So the last example is about a processor that is called Beta. Beta processor or Beta processor is basically a 32-bit processor. Okay, and let me tell you something about processors. The processor, any processor implements what is called instruction set architecture. So this is a very key word, ISA. This is a very key terminology that is used by the computer community, computer design community, or computer architects. And maybe you don't know it from this name, but if I write x86, then most of you will instantly recognize that x86. Okay, so x86 or AMD 64. Sometimes when you install different software, it asks you if your architecture is x86 or it is AMD 64, and that is basically the ISA or instruction set architecture. And this is the basically the ISA is basically an abstraction layer between hardware and software. You can think of it as a contract between hardware and software. So the hardware, the software only sees through the ISA. Okay, it does not see the detail of hardware. it only sees whatever the ISA makes visible to the software. So this is a very fundamental layer between the hardware and software, and this is how the software sees the hardware. Okay, the software only sees the instruction set architecture or ISA. Now this is you have seen so many processors of Intel. So starting from Pentium, from 486 we came to Pentium 1, 2, 3, 4, then Core 2 Duo, Core 2 Quad, and octa-core, and I don't know whatever, Core i7 and Core i9. All these architectures are basically implementing the same ISA, and that ISA is the x86. And that's the reason that if you run a software on Intel Pentium 1, it is still able to run on Intel Pentium Core or Intel Core i7, because the ISA is the same. Okay, so this kind of backward and forward compatibility, or forward compatibility to be more accurate, is due to the ISA. The ISA has stayed the same. Okay, that's why the executable can be run on the same ISA. But if you want to run an executable that is generated for x86 on AMD 64, you will not be able to run it because the ISA is different. So that's how important an ISA is. So whenever we want to design a processor, we need the instruction set architecture. And let me tell you that what is the instruction set architecture. Just one of the instruction, there are several kinds of instructions for beta, and you can search the web for that, but first is this one. We have the opcode, I think it is 6-bit. Then the RC register is 5 bits, RB register is 5 bits, and then we have this unused. So this is one class of instructions. This is class 1, and class 2 of the instruction is something like this. We have the opcode, which is 6-bit. Then we have the RC, then which is 5-bit. Then we have RB, which is 5-bit, and then we have 16-bit, which is our constant. Okay, so these are the 32 bits. So the one instruction is 32-bit. From here to here it is 32-bit. So each instruction is 32-bit. Then the opcode is 6-bit, which means that you can implement 2 power 6 different kinds of operations. Okay, 2 power 6 or 64 different kind of operations, and by operation we mean plus, minus, multiply, divide, or square root, or any other operation. So it depends on the opcode. So for example, maybe the opcode for this sum is 0, maybe the opcode for this is 1, maybe the sum code for this is 9, and so on. So this opcode tells you what operations you want to perform. Then we have 5 bits for RC or any register. So this means that there are 2 power 5 or 32 registers. Okay, and because the architecture is 32, the processor is 32-bit, then each register, 32 register, and each one is 32 bits. Okay, and each one is 32 bits. So every register is 32 bits. So that's some initial detail about the beta processor. If you want to study it deeply, you go to the website of 6.004 and you will have more detail about the instruction set architecture and kinds of instructions. Here we are more interested that given this architecture that we have on this slide, how can we code it? But let me slightly discuss the different parts of this architecture so that you understand it. Of course, this discussion will be not exhaustive, but it will be just a basic introduction. So maybe I will not tell you about all the signals or what they means, but I will tell you the basic ones. So this is the program counter part. Program counter is basically a counter that points to the instruction memory. So here is your program. So maybe you have written the program in C or C++, and then you generate the hex, and the hex goes to the instruction memory. So on each cycle, your computer reads an instruction, which is a 32-bit instruction from this memory, and the next instruction is 4 bytes away. That's why we add +4. So every cycle the PC is incremented by 4. So if it is 0, then the next cycle it will be at 104 to pick up the next instruction. Okay, so this is the purpose in life for a program counter. It just keep on counting with an increment of 4. This increment of 4 is sometimes disturbed when we want to implement a jump instruction. And jump instruction is the assembly language equivalent of a statement like this: if A is less than B, do this, else do this. So is this kind of statement is converted when it is compiled into jump instruction in the assembly language. So this is very important to have this kind of facility in your architecture, that the jump instruction can be executed. And you see that this one, this mux is used for that purpose. So sometimes the mux will be feeding PC +4. So this is PC +4 line, this is PC +4 line, and sometime it is doing something else which is coming from this line and it is going here. So this is, you see this adder. So we are adding something, so the current program counter, and then there is some offset that is coming from somewhere else. So this is how you implement maybe PC +100, for example. So it is coming from here. Then so this is the purpose and life of program counter and instruction memory. Then there is this very important file, register file. So all our 32, we said we have 32 registers and each one is 32 bits. So all of them are residing in this register file, and this register file is called 2-port register file, 2-port RF, because it has 2 read ports, RA1, RA2, and this is the corresponding read data. So here you apply the addresses RA1, RA2, and here you read data 1, read data 2. Okay, and this is the write address. The write address is same, so we have a single write port and we have 2 read ports. This is called single write dual read port register file. Then we have the write enable. It is controlled by this signal VRF, write enable register file. VRF stands for write enable register file, and this is the write data, which is the data that is coming from the ALU which we want to write in the register file. Again, this is the flag generation logic that we already discussed in some other form in the previous examples. Then this is the A cell mux, the B cell mux. This is our ALU, which can implement 64 functions. And this is the ALU func, which receives our opcode, which is 6-bit. This is the data memory where we store our data, and you see the data memory is attached here. So sometimes there are two instructions. One is load, which is like this, that you want to transfer something from the memory to the register file. So that is for that we use load instruction. Then there is store instruction, which is the reverse. Sometimes you want to transfer the register file into your memory. So by memory I mean the RAM which you have. So the RAM which you remember that you have 4 GB of RAM, or some of you may have 16 GB of RAM. So that's the RAM which you can increase and which you need for gaming. I'm talking about that memory. Okay, so with that memory there are two operations that are related. One is called load, which means that you want to load something from that memory into your register file, and you want to bring it closer to the processor so that processor can execute an algorithm on it. Or you want to store, which is the reverse. So there is something in the register file which you want to store in the memory. So these are the two basic operations. And if we just look at it, we see that if we want to store something, this line is coming from here. So write data, it's coming from RD2, read port 2. Okay, similarly if we want to load, then we read from here, and this comes to this path, and this is written here. So this is load. Okay, so these are some of the signals, some of the logic that I discussed, and this is the FSM, which has different signals generating all the muxes. And the logic for the control or the control FSMs depends on the instruction set architecture. But let me directly take you to the control table, which is somewhere down here. Again, sorry for the unarranged slide numbers. These are not serially arranged. So this is the control signals, or our FSM. So this is the FSM table. So this is one way to represent the FSM, and I hope that you understand that state transition diagram is one way and this is the other way. So these are different states or different instructions. Okay, so we have these are different instructions, are different states. So we have 1 2 3 4 5 6 7 8 9 10 states here, or different kinds. These are basically classes of instructions. These are not a single instruction. Maybe the op class has plus minus this, maybe this one has maybe NAND, or so these are classes. Okay, these classes are our states, and these are our control signals that goes to the data path, and these are the values of those. So in op class instruction, the WRF is 1, B cell is 0, WD cell is 1, and so on. You can check this with the architecture to understand how things are happening. But we are more interested that given this architecture, which is on this page, this is the main data path. So this one is basically divided in two parts. The one ID, this one basically denotes the memory. So we have two kinds, two memories, instruction memory and data memory. And then the other parts which are labeled 2 is your data path, and this one is called random logic. So a processor like this has 3 parts. Okay, processor design, it has 3 parts. One is memory design, which means how you design the instruction and data memory. The second is data path design, which is all the combinational logic and computational blocks. And the third is random logic. Okay, and again, if we talk about mapping it to ASIC, or if we talk about mapping it to FPGA, there are different methodologies to do it. For example, if we talk about FPGAs, we already discussed that we should map memories to block RAM. We should not map it to flip-flops because they are so expensive. Similarly, if we are talking about ASICs, then there are different kinds of memory cells for memory design. So we should consider a specific technology for the design of memories compared to data path logic. Okay, so I hope that you can understand the code, because the code is just a translation of the control table and the data path. So you should be able by now that looking at the data path, you should be able to write the code. This is very, very important. So maybe I gave you Beta processor, or I gave you MIPS processor, or maybe I gave you a RISC-V processor, or any processor, or maybe I just gave you a data path and consider it has no name, but I just want that you should implement or write the code. So from a language point of view, this is all what we need. You see that as a language, Verilog is very simple to learn, and it is basically the digital design part that is something that you have to understand. Writing the code is really simple. It is really systematic. If we talk about FSM, the FSM has code has 4 parts, and each part is very systematic. If we talk about the data path is very systematic. So I invite you to go through this code. This code is you should be able to understand this code. Given this table and all the things, you should be able to understand the code. You should be able to simulate it. You should be able to implement it on FPGA. It's a fun little, let's say, mini project for you. If you want to implement it, you have the boards in your lab, and it will be a very fun little experiment for you to learn. It should be interesting to know what is the maximum frequency that you can achieve, what is the maximum power consumption that that you can achieve, or minimum speed or maximum speed you can achieve. All these things are the results that as a digital designer you should be interested in. So this is all from my side, and this wraps up the section which we called digital design for Verilog HDL. So we discussed a lot of things regarding how to code. We discussed combinational logic, we discussed sequential logic, we discussed FSMs, we discussed microprogram state machines. So let me just make a list of those things. So we discussed list of topics under this digital design for Verilog. We discussed Verilog for combinational logic. Okay, all the things at the gate level, at data flow level, at behavioral level, how we synthesize it, what is non-synthesizable, I mean all of it. Okay, then Verilog for sequential logic, then Verilog for FSMs. Of course, I expect that you should be able to write you should be able to design state transition diagram for any FSMs. I will give you a detailed assignment for you to practice with FSMs. Then the fourth topic that we discussed is micro programmed state machines. We discussed programmable architecture, and we implemented a factorial program on this. So this is basically the fundamentals of how computers work. Then we discussed examples. One example was GCD, the other example was beta processor, and I expect that you should be able to read and understand the beta code. Okay, so these are all the things that we have discussed, and I wrap up this section. And if you have any questions, please study the material, watch the video lectures, and you can ask me in the question and answer sessions, and you should try to solve the assignment yourself, and there will be a quiz in these topics, maybe the coming Friday. Okay, so good luck.